Okay, let's move on to the next method of graphing polar equations, which is if we understand some things about symmetry of polar equations, then we can save ourselves some time if we're graphing them. Okay, so I made this little chart for your notes if you want to write these down, if you follow along. If we have a function of cosine, if we have a cosine function, we could have a scalar here, a scalar inside. Notice I'm not adding or subtracting anything inside there. That'll mess up the symmetry. And then I can add or subtract anything after that cosine. Any function that looks like this will be symmetric with the polar axis, which is just the x-axis. In other words, anything that happens above the x-axis will happen below the x-axis. That will be a line of symmetry. And remember, when you're in the polar world, that's called the polar axis, right? Where 0 degrees is. So you might remember this picture here when we graphed, when I just showed you real quick the graph of cosine theta, that circle is symmetrical with respect to the x-axis. Okay, so we know that's true about any variety, any of these type of varieties of the cosine function. It'll have that symmetry. If you want to see a proof of that, it's on page 543, okay, of your book. You guessed it, if you have a sine function with a scalar inside or outside or a c value there, moving the wave function up or down, that will be symmetrical with the y-axis, or the line theta equals pi over 2, which is this vertical axis, okay, which I just drew a little picture of that circle that we graphed in the last video, okay, symmetrical with respect to the y-axis. All we have to do is graph one side of our graph. The other side is just a reflection of that. Okay, so you see how this is going to make graphing easier. Okay, the next type of symmetry, which you don't run into very often, is symmetry with the pole, or symmetry with the origin. Now, you remember at odd functions, when you're back in rectangular space, odd functions have symmetry with the origin. And the simplest way that I could think of that you guys might understand, there's lots of other ways. You could look on page 543, like I said, if you want to get a better, more details about this. For every r theta, there is a negative r theta also on the graph. Basically, for every point, there's a point directly opposite of it through the origin. Okay, I'll show you what I mean by that. So let's suppose this point right here is r theta. Okay, there is a point on my graph that is directly opposite, same theta, opposite r, right? So theta is the same, but now I have a negative radius. So there's my negative r theta, and it happens for every point on my graph. There's a point that's directly opposite from it through the origin, and that makes it a graph with polar symmetry. It has symmetry with the pole, which is just the origin. Okay, so that's an easy check. If you graph it and you want to know, does it have symmetry with the pole, you just look at that. Does every point have a point that's opposite from it, same theta, opposite radius? Okay, so that's how I would check that. Okay, let's move into an example. How can we use this to our advantage? Let's suppose we had to graph this function, 1 minus 2 cosine theta. Now, in the last video, I made a super long chart. I guess it's right here. I can show it to you. We had to do all these inputs and outputs to graph sine theta. Okay, it turns out we only have to do about half of this. Well, it's pretty much half of it, because we know that it's symmetrical. Okay, this is a function of cosine theta. It is in this form, right? So we know it's going to have symmetry with the x-axis, or the polar axis. So really, we just need to graph one half, and then the other half we can figure out as just a reflection. Okay. So would you guys like to do the upper half or the lower half? I would rather do the upper half. Okay, so which points should we graph? Well, the upper half is all the angles of theta from 0 all the way to pi. So let's make a chart where we have theta and we have r, 0, and we'll go pi over 6, pi over 4, the same old angles we always do, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. I know you can't see, I'm off the screen now, but. So I'm going to use my calculator to calculate, plug all of these theta values into my function for theta. and I'll just use my calculator to generate the R values, and I will have that complete in 3, 2, 1. Boom! There it is. Just used my calculator to plug in these theta values, and you might notice that I rounded them to the nearest tenth, and I did all the common angles from 0 to pi. Now let's start graphing. Now notice this is half as much as we did last time, okay, because we have symmetry to help us this time, so it saves us some time here. So 0, -1. Theta is 0, so I'm facing this way, right, along the polar axis, and I have a radius of -1, so that means I got to go backwards by 1. So what do I want? How do I want to scale my graph? Well, I notice that the largest value it takes is 3. The largest value R will be is 3. So I'm going to let that be this, this furthest circle on my graph so that I don't have to try and fit my whole graph inside of just 3 rings. So I'm going to call this 3, which means that 1, 2, 3, yeah, so this is 2, and this is 1. Okay. So 0, -1. 0, I'm facing that way, I go backwards 1, so that would be this point right here. And then pi over 6, -0.7. So pi over 6, I'm facing this way, -0.7 would be backwards, so maybe right here. Okay. And then pi over 4, -0.4. Pi over 4 is this angle, -0.4 would be maybe right here. Okay, so I've got this little curve coming in here. Then we go to pi over 3, 0. Well, it doesn't matter what direction I am. If my radius is 0, I'm going right through the origin there, right? Pi over 2, 1. Pi over 2, now I'm facing straight up. And 1 is my point, so I got one right there. So that's what my curve has done. Okay, let's see what happens next. Pi over 2 pi over 3, 2. 2 pi over 3 is this angle. Now we're at 2, so there's that. 3 pi over 4, 2.4. 3 pi over 4 is here. 2.4 might be right there. Okay, and then 5 pi over 6, 2.7. 5 pi over 6 is this one. 2.7 is probably right there. And lastly, pi 3. Pi 3. So I get this kind of spiral looking thing. I'll just connect the dots. Okay. Now, I can be done plotting points because I know that each of these points is going to be reflected and have a mirror point on the opposite side of the x-axis. And I know that because that's true about any cosine function graphed in the polar graph. Okay? And it has to do with cosine being an even function. We know that if we graph cosine in rectangular coordinates, it's symmetrical with the y-axis, so that makes it symmetrical with the polar axis here. Okay. So how do I reflect it? Well, I just take each point and reflect it up or down, depending on which side it is, across that x-axis. Okay, so this point right here is going to end up, well, let's see, right here, I think, right? Yep. This one goes here. This one goes here. I'm just reflecting each point one at a time. This is an easy one. It's just one above, so that becomes one below. And then there, and then there. So we'll continue our curve around, and we get this shape. This shape has a special name. I forgot what it is. If you care, you can look at page 543, limaçon. So funny, I don't know, some kind of French word. Either way, these shapes actually are, when it comes to certain like areas that microphones will pick up sound and stuff, these shapes are actually what will outline the area, the shape of the zone where the microphone will pick up or detect sound, as well as other things. But that's just one application I happen to know of. Okay, so there it is. There was our graph. We used what we knew about symmetry to just graph one half of it. And of course, if it was a sine function, you would graph either the right side or the left side. You pick, and then reflect it from there. So there you go. That's how you graph using symmetry to cut down on some time and some calculations. I will see you guys in the next video.